Good day, and welcome to today's Electronic Design webcast. Our topic today, improving battery management systems with high accuracy shunt current measurements, sponsored by Bourns. I'm Bill Wong, Senior Content Director with Endeavor's Design and Engineering Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. This webinar interface allows you to resize the presentation by clicking on the maximize icon or by dragging the lower right corner to enlarge the window. Additionally, we welcome your questions during today's event. We'll answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speakers. Matteo Bosio is a field applications engineer at Bourns, responsible for technical support in the EMEA region. He has more than 15 years of electronic engineering experience. Johan Skiffner is a technical marketing manager at Bourns, responsible for marketing and technical support of sensing products. He has more than 10 years of engineering and marketing experience within the sensors industry. You can learn more about our speakers by clicking on the blue speaker bio widget on your console toolbar. Now let me turn things over to our presenters. Gentlemen, the floor is yours.
Thank you, Bill, for the introduction. This is Johan speaking, and thank you for the audience for joining our webinar today. We will be speaking on the latest trends and requirements for current measurement and battery management systems. The focus will be on the current measurement with shunt current sense resistors. Furthermore, we will give a quick overview on the Bourns product portfolio for battery management systems in general. So looking at the agenda on today's webinar, we first will give some background on the company Bourns. Then you will give an introduction to battery management systems, looking into detail on the current measurement of the battery management system, and explain a little bit the link from current measurement to system performance, and show how improved current measurement can help to enable safety, influence the lifetime of the battery, and to generate reliable user information. And of course, you explain that based on the Bourns current measurement solutions. Looking quickly at the Bourns, the company Bourns, which was established in 1947 by the co-founders Marlon and Rosemary Bourns, and it's still privately owned by the Bourns family. The headquarters shown in the picture here, a clear blue sky, is based in Riverside, California, close to Los Angeles. Bourns has a worldwide presence with engineering, manufacturing, and sales locations around the globe, and is working in several industries like automotive, industrial, infrastructure, communications, medical, consumers, and others. Our vision is to be the company our customers think of first for reliable electronic solutions. But now we will have a look at the portfolio from Bourns. So the Bourns portfolio consists of mainly three major product groups, the Bourns Component portfolio. We have the circuit protection portfolio, having three subgroups: over voltage protection, over current protection, and over temperature protection. The over voltage protection has technologies like Resistor technology, gas discharge technology, and semiconductor technology for thyristors and TVS diodes. In the over current protection, we are having melting fuses, resettable fuses, and electronic fuses, all kind of different fuse functions. And then we have a group of over temperature protection products, which are typically used in small battery packs. Those are mechanically the bimetal disc activated switches. The bimetal disc is activated by a temperature and opens and closes the contact for over temperature and over current protection. And the next group in the portfolio is the power conversion portfolio with inductors, transformers, filters, and other magnetic components, mainly for power and signal applications. And this group, again, is split into two subgroups. We have the first group called the standard magnetics, and the second group called our custom magnetics. And the standard magnetics are products typically available from a data sheet or from a catalog. Here we have, for example, inductors for DC-DC converters, for filtering. We have a number of common mode chokes. We have signal transformer, some power transformers as well. And then in the second group of our custom magnetics, we have a lot of capabilities available to offer customized products based on the application requirements. This can be inductors, this can be transformers, this can be transformers for power, for signal, like the typical flyback, forward transformer, etc. And typical special requirements can be increased isolation levels, high current, etc. And then we have the last group of products in the Bourns portfolio, Bourns component portfolio, which are the sensing products. And here we have the first group, our traditional trimmer and potentiometer products for user input, but also for linear and rotary sensing applications. We also have non-contacting sensors and also non-contacting encoding products. The next group would be our environmental sensors, which are sensors to be mounted on the PCB, and those consist of pressure sensors and humidity sensors. And then the third group, or the last group in this sensing portfolio of Bourns, are our resistors. And part of the resistors are, of course, the Bourns current sense resistors, which will be an important topic of today's webinar. After looking into the company Bourns and the product portfolio, I would like to give a very quick introduction overview about battery management systems. What is a battery management system and what is it doing? So the battery management system is typically used to manage a battery, because a typical battery of today, cars, industrial applications, etc., are using battery packs with a number of cells. And the battery management system is there, as shown in the block diagram below, to offer a lot of functionality to manage that cells, to monitor the status of the cells, and just to ensure the safe operation of the system, of the battery system, and to maintain the optimal usage to allow performance and lifetime of the system. So the sub-functions of the battery management system include measuring, for example, of voltage, of temperature, of the current in the battery system. It has to disconnect the battery in case of a failure, in case of an overcurrent, of a short current, for example. It has to disconnect to prevent damage or to prevent hazard. It's balancing the cells, so it makes sure the cells are equally charged and discharged. And it's calculating battery status information based on the measured values, and it's communicating that status information to the system, like the car or the energy storage system. And those kind of battery management systems are typically used in applications with an increased or higher need for energy. So we're talking about electrical vehicles like the EV car, talking about residential and industrial energy storage systems. Are we talking about heavy transportation? For example, forklifts are using, or electrical forklifts already established over years, decades. But we're also seeing more and more applications in agricultural, construction equipment, and even mining. So coming from the battery management system, let's have a look what kind of Bourns products are used in these kind of systems. So Bourns components are used all across the battery management system. If we start with our magnetics, they are typically used for power conversion functions, for isolation, and for filtering. And there are a lot of our catalog products like isolation transformers, inductors, and for filtering and DC-DC converters or for power transformation are used. We have a lot of standard common mode chokes for the typical communication protocols like CAN or SPI. And we also offer customized products with special requirements, for example, for the high isolation levels required in the battery management system. Then we also offer a lot of circuit protection products for overvoltage and overcurrent protection, which are suitable and used in battery management systems as well. We are offering here the fuses to disconnect the cells from the system in terms of an overcurrent. We have a lot of We can offer small power TVS diodes for overvoltage protection, as well as high power diodes for higher surge events. So the Bourns circuit protection products are distributed all over the battery management systems. And then, last but not least, we also offer our current sense resistors, our shunt resistors, into battery management systems from the catalog up to 1000 amp current rating, but with many options for mechanical and electrical customizations and added features. And then below that gray box, we also have our previously mentioned over temperature protectors, but those are typically used in small energy battery systems, like in portable electronics, like tablet computers, smartphones, and others. After looking into the general Bourns components for battery management systems, let's have a more detailed look into the current measurement functionality and requirements in a battery management system. The main function of the battery management system is to monitor all current flowing in, so the charging current, and also flowing out of the current, so the load current of the car or the energy storage system. And this is necessary to maintain and to provide the right information for safety. So the system has to disconnect the battery. The battery management system has to disconnect the battery from the connected system in terms of an overcurrent, an abnormal condition, to prevent malfunction or hazards. It has to protect against overload to prevent damage of the battery or other components. It's important, the current measurement function is also important for reliability, to maintain the lifetime of the battery through an optimized usage of the charging and discharging cycles, because the charging and discharging cycle have a heavy effect on the aging of the battery. And optimizing those and have them under control means to maintain the battery life or even longer the battery life. And then, for performance reasons, small errors and small tolerance of the current measurement allow to utilize the limits of the system to drain the full current, for example, and it reduces the need for safety margins at full performance. And then, last but not least, for comfort. And this might not be something somebody would think about first when discussing current measurement. But as you will see a little bit later, some of the information provided to the user of an energy storage system or of an electric car is calculated based and dependent on the current measurement function. What are the requirements for current measurement in battery management systems? So first of all, we would like to have an accurate current measurement over the full range. So we would like to measure from small currents, which can start in the milliamp range, up to the full-scale current of the system, which can easily end a few hundred up to 1,000 amp, for example, for industrial applications. And in today's requirements, what we see in the market are customers or applications are looking for accuracy ranges around and below 0.5% over the full temperature range. To allow an accurate measurement in the milliamps range, it's important to have a very low offset error. For example, we're giving here a number like less than 100 milliamps, which is quite a small number if we look at the current range up to 500, 600, or 1,000 amps. So the low offset error is quite a demanding requirement for the current measurement functionality. And also, the current measurement has to be stable, not just over temperature, as said before, but also over the life of the system. And then, as battery management systems are used in electrical cars, but also in heavy transportation and for example, construction equipment, those systems need to be robust against mechanical stress like shock and vibration, but also against external magnetic fields, for example, like the traction motor or other electrical motors in the system, in the car or vehicle, and also, for example, against power switches. So it's important to have a robust measurement. And then another very important point is the isolation barrier between the power and the signal subsystem in the battery. Today's EV car batteries are working at around 400 volt. We can see already high-end cars using batteries up to 800 volts. Manufacturers like Porsche and Aston Martin, for example. But we see others following that trend. So we see Volkswagen, General Motors, Rivian, Hyundai, and others to go up to the 800 volt. And in some applications with a high demand for current, for example, in mining, we also see applications in the kilovolt range. So those are some of the requirements for the current measurement in the battery management system. And with the next slide, I would like to give some background of one important acronym when talking about the battery status and the battery management system to calculate that value. And that the one I'm talking about is the SoC, or state of charge. That is the information about the filling level of the battery. It's expressed typically in a percentage from 0 to 100, and most of you might know that from an information on your cell phone, like on the picture on the right-hand side. So it's just an information how much, which level is the battery charged or discharged. And to calculate that information, so the state of charge, it's very important to have an accurate current measurement, because a typical principle to calculate the state of charge of a battery or the filling level is the so-called Coulomb counting. And the Coulomb counting is a technique which measures all current flowing in and out of the battery from milliamps to the full-scale current range and integrates that over time. It means even a small error in the milliamp range integrated over a long time can lead to a significant error. So the state of charge information requires quite an accurate current measurement to allow to estimate an accurate SoC, or state of charge information. And that value, the state of charge, is used, for example, in an electric car to just show the user and the fuel level or the fuel gauge for the electrical car, or to calculate the range which the car can go with the battery level, the battery charging level. So it's quite an important measurement or calculation, which is very dependent on the current measurement performance. What we've done internally is we have done a simulation to show the impact of the error of a current measurement system, or the current measurement to the SoC calculation. What we've done is we used a maximum current of 600 amps at a 500 amp hour battery, and we used the UDDS standardized drive cycle, emission test drive cycle, and generated based on that drive cycle current profile, which is shown on the top right-hand side diagram. So this profile goes from up to 600 amps. It takes around 23 minutes and represents an urban route of around 7.5 miles. So it's not that long, it's quite a short ride. But over that profile, we can see already an evaluation of errors based due to the offset error and due to the percentage error, which is shown in the diagrams below. So an offset error of 500 milliamps results in around 0.6% error of the SoC calculation. But an offset error of 500 milliamps at a 600 amp full scale means it's just 0.08, around 0.08% error of the full scale, but already results in 0.6% error of the SoC calculation. And then looking at the percentage error, 2% error would result in around 1.1% error of the SoC calculation over that test cycle. Those numbers are looking small, but this is only for 23 minutes or 7.5 miles. So these errors can add up over time and can lead to wrong information about the battery filling level or the car range or the energy stored in the energy storage system. So to provide good information to the user, reliable information to the user of the car or the energy storage system, it's important to have an accurate current measurement system implemented. And with that, talking a little bit about a background on current battery management system and the current measurement, I'm handing over to my colleague Matteo, and he will look a little bit deeper into current measurement technologies and especially in shunts.
Thank you, Johan. Good morning, everybody. Let's have a look to the current measurement technologies used by BMS designers. We have mainly three solutions: shunt resistors, all effect current sensors, and flux gate current sensors. Talking about shunt resistors, this is a very accurate solution. You can reach up to 0.5% accuracy. And this is also a solution with a very good long-term stability in terms of linearity and low offset risk. This is a solution not susceptible to external magnetic field with a faster response. That is very important in you have to protect from overload or short circuit. This is typically a cost-effective solution. On the disadvantages, we see that this is a not isolated solution, so you need a further circuitry for having an isolation. This means power losses because it's a resistance, a very low value resistance, but your resistance with current. And this needs a signal conditioning circuit. Speaking about the all effect current sensor, this is an isolated solution with low energy losses and also is a cost-effective solution. But on the disadvantages, we have the accuracy. This is typically higher than the previous solution, so in the 2–3% range, with a limited linearity and also an offset error temperature dependent. Speaking about the flux gate current sensor, this is an isolated solution too, with a good accuracy, similar to the shunt solution, and also with a low offset error. But typically, this is an expensive solution and also very susceptible to magnetic field. So what we are seeing now, due to the increasing current measurement accuracy requirement, we are seeing a migration from the all effect based solution to the shunt solution. Now, let's have a look to some technical consideration about how to correctly integrating a shunt into a BMS. In this case, we have a shunt, a resistor on the PCB, and you have the current flowing into this component. But the voltage drop is not only the voltage drop due to the resistive element, but there you have also a voltage drop due to the lead and solder joint resistance. When you speak about the resistive element, we know very well the behavior of this part. But when it comes to the lead and solder joint resistance, this is a less predictable behavior, and also with a higher PCR and resistance change from board to board, so it's something difficult to manage. So it's necessary to find a way to get only the voltage across the resistive element in order to have a better measurement. The solution is the so-called Kelvin principle or 4-wire connection, and this can be implemented. This means to have a separate sense and current load traces. This could be implemented on a two-terminal shunt, so you have the separation of the traces, and you have the internal traces for the sense, or you can have a 4-terminal shunt. In this case, you have 4 pins, 2 for the power, for the load current, and 2 for the sense. In this case, we have our family, the CSS4J, that has 4 pins. But also, if you look on the bottom at our power shunt, we have the 2 power connection with where there is the holes for the bolt, and we have the 2 pins for the sensing connection. Another topic to consider is, in order to reduce the error, is the 3 sense pin connection. This is a solution for reducing the error due to the ground current. So in this case, you add a third path in order to avoid problems with the ground current, and and you can you won't have a voltage drop due to the current you don't want to measure. And you can see typically you can have this is what you when you see three shunt with 3 pins, that's the purpose. So how to implement the Kelvin connection? Here we have some typical example. We can connect the shunt to a PCB through screw or through SMD with a solder probe via solder pad, using through connection, using riveting pins that could be connected. You can have a connector, you can solder to a board, or you can solder wires, or you can also have a wire directly soldered, to the shunt. So after considering the sense connection, now let's see the power connection. So when you have a high current passing through the shunt, it's very important to have a low resistance connection point, because the higher is the connection resistance, the higher is the heat created, and here you can have a problem with the dissipation, and this can also affect the longevity of the device, and maybe also bring to some interruption in the connection in case of bad dissipation. On the right side of the slide, you can see two typical connections. One using cable with lag on the top, and on the bottom you can see the connection between a shunt and a bus bar. In this case, you have to take care of the contact surfaces. These surfaces could be uneven or could be covered by isolating impurity layer. And the true contact area at the end of the day is made by microsurfaces, and this reduction of the contact area brings to higher resistance and hence higher heat created. So it's having a very good quality shunt and very good quality bus bar brings to high efficiency connection. So we have two parameters to consider: the contact pressure and the contact area. So looking at the graph, we have the behavior of the contact resistance over the contact force, so the tightening torque. So we see that increasing this tightening torque, you have a rapid decrease of the contact resistance, but till a certain point. And a too high tightening torque can also lead to distortion, and distortion brings to reduction of area. So, and this means higher resistance. So you need to find the right tightening torque, not too high and not too low. Also, it's advisable to distribute the pressure by increasing the number of tightening points. And also you have to consider the bolt material, because you can have expansion, corrosion. So there is several topics to consider. About the contact area, in the picture on the right, you have the light blue area, that is the overlapping area between the bus bar and the shunt, and you have the red area, that is the cross-section area. A common rule is to have the overlapping area higher than 5 times the cross-sectional area. And this because if we look also in the graph, where we have the behavior of the contact resistance over the ratio L over B, and at the end of the day, L over B is the overlapping area over the cross-section area. We see that if this ratio is 1 or lower than 1, the resistance is high. But if this ratio is higher than 5, we see a decrease. This because when you have a limited overlapping area, the flow of the current is not uniform and is very concentrated at the edges. But if you increase this overlapping area, you have a more uniform flow of the current, hence a lower resistance and a better efficiency. Here we have the 3 typical connections for bus bar to shunt. We can have a bolted joint, is the the most common, but we can also have a riveted connection that is a bit more difficult for installation and for maintenance. And we can have also the clamping joint. Here you have two external clamps, and this is let's say a more efficient solution because you don't have bolt holes, so the current flow is more uniform and is not disturbed. But here you have to add components, and usually brings to higher cost. After considering the electrical and mechanical connection of the shunt, now let's see how to manage the voltage signal coming from the resistor and how to deal with the error. We have typically we have two levels of error. One error due coming from the resistor itself, and one level of error coming from the circuit for the signal conditioning circuit around the shunt. When speaking about the errors coming from the resistor, you have the tolerance that could be 1%, 5%, and can be easily compensated in the calibration stage. You have the long-term drift effect that are typically low in the shunt, and you have the temperature effect. We have the TCR, so the change of resistance over temperature, and the thermal voltage, so the thermal EMF, the thermal effect. Speaking about the signal conditioning errors, we can have errors due to the signal path on the board that could bring to add overall current measurement. We can have noise on board, maybe due to switching power supply or some other devices. We can have thermal effect, long-term effect. We can have also errors due to the amplification stage, and we can have also noise pick up from radiated sources. And in this case, it's also very important to pay attention to the layout. So now let's have a better look to the two temperature effects, so the TCR and the thermal EMF. So TCR is the temperature coefficient of resistance. So it basically is the changing of the resistance over the temperature. This is data that you can find in the data sheet. It's typically in part per million over degrees. And if we consider a measurement a current measurement in 2 moments, when you have two different levels of temperature, so you can have a mistake due to this temperature difference. So if you're considering a temperature of 30 degrees C, in two different moments, you can have 0.45% error. But knowing the behavior, as we can see on the left bottom, the behavior of the resistive element over the temperature. So, and placing a temperature sensor on the resistive alloy directly, so we have the temperature signal and we have the voltage, the measurement voltage. So using, for instance, a microprocessor, is easy to compensate this error because it's a repeatable error. Speaking about the thermal effect, this is a voltage typically in the order of the microvolt, and is due to the temperature variations across the resistor. So you have a junction between the metallic resistive element and the terminals, and this is a thermocouple. And the thermocouple generates a voltage proportional to the temperature across it. So this thermal EMF adds an offset error to the measurement. Also, the thermal EMF parameter is you can find it in the datasheet. Here we have an example for this model. Is 0.25 microvolt over Kelvin. And in this example, if we have a 10 Kelvin of difference of temperature drop with 50 microns, at the end you have a 50 milliamp of offset error. You have also to consider the connections. For instance, using steel screws can add like a new thermocouple, and this could bring additional thermal EMF drift. Here we have our typical shunt where we can have the bare copper, we can have plated, pre-plated or fully plated shunt, and depending on which parameter is most important for your application. For instance, considering a pure bare copper shunt, you have a better temperature coefficient, TCR, but the long-term stability is not the best. While if you use a fully plated solution, you increase the long-term stability, but you can have a lower TCR. A worse TCR. So also for this, we have different solutions based on the. So now I hand over to Jochen that he will explain how to select the right component and also our solution.
Thank you, Matteo. After talking about the battery management system, current measurement, and the technology, we're looking into selecting a component for the application. So the first thing we have to do is define the measurement requirements. So the shunt current measurement is typically a trade-off between power losses and signal output. That means you would like to have a good signal output to be used on your controller or input, but you also want to have as low as possible power losses at the shunt or the resistor itself. So the lower power losses means you would be looking for a lower resistance, while increasing the signal voltage would ask for increasing the resistance. Therefore, it's always a trade-off between those two parameters. How do we go forward with the selection? So first, we look at the current in the application. And there we have two things we require. We have the peak current, or the peak current we want to measure. And then we have the continuous current. That's the average current, which is used to calculate the average power at the shunt. The next thing is calculate the shunt resistance. To calculate the shunt resistance, we typically use the input voltage of our following signal conditioning and calculate which resistance is necessary to generate the right voltage drop or voltage here with the shunt. Therefore, our signal conditioning defines the output voltage of our shunt and therefore the resistance value of our shunt. With that resistance value, which we calculate, and our continuous current, we can calculate the average power at our component, at our current sense resistor, for selecting the right size or the right power rating here. And in the blue box on the right-hand side, I have an example here. So if you say we have 1,000 amp maximum readable current and continuous current of 200 amps, and then we have our ADC with an input range of plus minus 200 millivolts, we would use the 200 millivolt input range and the maximum to be measured current to calculate our resistance, in this case 200 microohms. And with that 200 microohms, we use our continuous current, the 200 amps, to calculate the power at the component in the application, or the heat generation at the component in the application. And in this case, it would result into 8 watts. So we calculated based on the current, our signal conditioning, the necessary resistance and power rating for the shunt to be selected. Now, with that information, we can go into the component selection. We typically start with the power rating. So we calculated this at 8 watts. What we would do is we would check if we have some worst case condition to be taken into account, like an overload or power derating, which should be respected. But based on the power rating, we use the product family. And in this example here, I'm using the CSS2H5930 series from Bourns, which offers at the resistance range of, or at a resistance value of 0.2 milli or 200 microohm, a power rating of 15 or 10 watts. Why do we have two different power ratings on the data sheet? I mean, if you look at the picture in the center bottom, this should show where the energy or where the heat is going on the shunt resistor component. So the heat and power dissipation happens mainly through the shunt terminals and the PCB. Therefore, the heat and power dissipation capabilities of the PCB current path, or let's say the thermal conductivity of that path, defines the power handling capability of our shunt component. So the majority of the heat is transferred through the terminals. Just a very little part of it is dissipated through convection, through air, shown with the small red arrows. Therefore, we have to consider the component and the PCB for the power rating. And we define in our data sheet here 2 temperature points and combine a power rating for that temperature point. If the component heats up to 70 C, at 15 watts, we can drive, if you drive 15 watts via the component and the surrounding PCBs, lead to a self-heating up to 70 C, then we can have 15 watts of the component. If the self-heating increases, then we can go into the diagram later in the lower section in the data sheet and check which power can be handled at that temperature range. Therefore, for selecting the component, we have to know power rating, and we have to know or have to simulate the heat dissipation and thermal conductivity on the PCB or on the circuitry as well. So after that example, to select a shunt and what to be considered, we have a quick look at the Bourns portfolio. The Bourns portfolio offers a range of current sense resistors from chip up to already discussed EB welded metal strip types, looking like a copper bus bar. The power range ranges from around 2-3 watts for the thick film chips up to 50 watts, and we allow currents up to 1000 amp and the highest power, lowest resistance rating of the EB welded types. A little bit on the technology. The foil types, the metal foil types, using like a thick film chip substrate with a small layer of metal. We call it a metal foil. Typically at low resistance and metal with a low TCR, in the 50 ppm range. For small double-digit currents, double-digit amp currents, we have the metal strips with our metal plate with a little overcoat for protection and some soldering finishes on the 2 terminals. And both chip types are available in a standard package, but also in the so-called white terminal package. And this white terminal package is shown on the bottom of the slide. The white terminal package allows more heat dissipation through the terminals into the PCB. Therefore, these white terminals can handle higher power, the same dimension as a short terminal package. And then we have the welded types. Copper terminals welded to specific resistive alloys with low TCR performance, high TCR performance, low TCR drift. We have the CSS types, which are SMD types, typically soldered to a board. And we have the CSM types. You can see it on the mounting holes. Those are a little bit bigger, typically screwed to copper bus bars or to cables, etc. Looking into the general key features, the resistance range goes from 25 microohm up to 100 milliohm. We have a catalog here. We can also customize those resistance values. The power rating goes up to 50 watt in our catalog for these biggest size copper bus bar types. Thanks to the design, we have a very low inductance for kilohertz measurements. We are using materials with low thermal EMF, so low thermal voltage. Our resistive materials are typically below 50 ppm per degree Celsius, and especially the welded type components having a very wide temperature range from -55 to 170, and are quite robust against overload or pulses, etc. So after that level, looking into the standard portfolio, we give a quick overview of our customization options. On one hand, we can offer customizations on the shunt component itself, so we can offer different sense pins, different dimensions, different platings, resistance values, just based on your or the customer's or application requirements. But we also offer more and more of these shunt current sense resistors with an added PCB and a temperature sensor. And that temperature sensor in this design is reliable, placed on top and repeatable position of the resistive alloy. And this temperature signal from the NTC can be used to compensate for temperature drift of the shunt material and therefore further improve the accuracy of the current measurement. Now with Bourns, we're looking forward in the future, and we're looking into an evolution from a resistor to a sensor. So we're looking into going the path from a passive component to a sensor solution or sensor module. And if you look at the typical trade-offs of a passive component, it doesn't have the isolation. It does have power losses through to the resistance and current and voltage drop, and it only offers typically a millivolt output. Therefore, it requires signal conditioning and cannot be used directly. If we go further, looking into a sensor, we're still talking about the current sense sensor using resistive technologies or shunt-based sensor. But this solution has integrated signal conditioning. This signal conditioning is using the latest designs, latest available products to allow low millivolt input, therefore reduce the losses or the heat generated. We add an isolation barrier to provide the isolation between the load or the power and the signal stage. And we are able to offer amplified or digital outputs. And how can this signal conditioning be integrated into the shunt sensor? There are typically two ways. The first way is just to use an isolated amplifier or ADC, and then have an isolated signal output of raw data, so amplified shunt voltage or a digitalized shunt voltage. This typically can leverage high update rates and a fast response time. The available data or the output data is typically raw data. The second option would be isolated communication. And what I mean with isolated communication is we connect signal conditioning circuitry to the shunt, do a temperature compensation, do calibration, do thermal EMF compensation, etc. And then after all that calculations, we transfer it via CAN to the system, to the connected system, and that CAN communication has a CAN isolation barrier. So we isolate the data or the CAN communication and provide ready-to-use data to the user. Of course, this can achieve much higher accuracy, also by compensating offset and temperature drifts, etc. So this is looking into high-performance current measurement, but that takes it takes some time, so the response time and the update rate are slower. How can this look like? Especially for battery management applications on which we think it's important to have a very low error of the current measurement, but we don't need a measurement up to the hundreds of kilohertz. Therefore, we're working on a prototype currently, or you've seen the picture before, with a shunt using an integrated signal conditioning, doing a temperature compensation, doing an offset correction, also correct the offset through to EMF. It offers the isolation barrier in the required levels, can be up to 1500 volts, and we offer digital output. And this does not have to be CAN bus, it can also be SPI or others. The accuracy is below 0.5% over the entire temperature range. And this can even be advanced with special calibration. And we also have some additional features in the catalog, like voltage measurement. We can optimize it for the application current range. We can offer different output functions as well as can be output communication, or can be also IOs like switching outputs, etc. for over current signaling. Okay. After that shunt module, a little bit looking in the future, let's summarize the webinar of today. So an accurate current measurement in the battery management systems enables the comfort with precise battery status information for the user. Can be driver, can be user of the energy storage system. It helps and improves with reliability by enabling and optimizing, for example, things like smart cycling. It helps with the performance just by maintaining the small errors, allowed to go to the limits of the system, and don't have extra errors in high temperature worst case conditions. And then with the Bourns portfolio, the Bourns shunts can help to improve the current measurement accuracy. The Bourns custom shunts can be a tailored solution based for the typical applications, for the application based on your requirements. And then the Bourns coming shunt sensors, shunt-based current sensors, will offer high performance with a ready-to-use output and a simplified implementation. So with that, thank you for your attendance so far. We are going now into question and answer session, and hand over to Bill.
Thank you. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, type your question into the question window on the side of your screen and then hit the submit button. While we're answering your questions, please complete the feedback form, which is located at the bottom of your screen. So to start with, are these products for battery manufacturers only, or can anyone building electric vehicles have access to them?
Sorry, I did not get the question. Could you repeat it, please?
Sure. Are these products available only to battery manufacturers, or can anybody building electric vehicles have access to them?
These are really available to all of our customers. If you want to become a customer, you can buy them as well.
Okay.
What
is the bandwidth of the isolated current shunt solution?
We're looking, as we're using CAN in the prototype, of course we're limited by the CAN bandwidth. We're looking into having I mentioned the I/O, the switching output for overcurrent detection or peak detection. But today, with the solution based on CAN, of course, we're limited in with the CAN communication, and I think there we're talking more about single kilohertz. But we can go into detail and offer other options as well.
Good. Next question is the thermal EMF due to the Seebeck effect?
Yes, it is exactly the Seebeck effect of the thermocouple. Yeah.
Okay, I think this may be with respect to slide 24. Why is the EB welded shut, and is it slightly curved?
Slightly curved. I mean the EB welded metal strip on the right-hand side is slightly curved to allow soldering of the terminals without touching of the resistive alloy to the board.
Okay.
And to give some margin for the welding joint.
Sounds good. What is the temperature range for your solar setup?
We can go in the page where we show our shunt. Right. This is the temperature range for our shunt. So, what is this question? What we can say is our operating temperature range, and this is the -55 to +107. Maximum continuous operating temperature.
All right. Next question, what is the shortest pulse current your shunt can measure?
That depends on the...
Yeah, please.
That depends on the inductance or the parasitic inductance of the components. If we have a flat component without curves in the terminals, it can be into the hundreds of kilohertz range. If we have like a shunt resistor with bandings, etc., this can be lower. But it can be at the kilohertz range, hundreds of kilohertz range, optimistically above a megahertz.
Okay, I got a two-part question here. Can these current sense topologies be used to sense the presence or absence of a battery connection? And the second question is, will batteries always draw some charge current, or will they eventually drop to zero?
This okay, shunt is a resistor. So this just measures the current flowing to. So can this? Yeah, if the you have the offset error, that is the error without current, that is very limited, but this, I don't think this depends by the current sensor. If the battery can detect it. Yeah, the battery just say the current passing in the path. So
Yeah, I would agree. It's a current sensor. If there's a current flowing in and out of the battery and it's inside the measurement range of the sensor, it can measure it. But if the current is on idle mode and if this battery is, or the system is in idle mode and no current is flowing in or out, these sensors cannot detect if the battery is connected or not.
All right. Which material is recommended for bus bars, and what are the secondary manufacturing processes on it, and why?
bus bars are typically made by copper. And from our side, I can answer about the shunt side. So, and I don't know, Johan, if you have something to add about the bus bar side.
I mean, on the bus bars, if the shunt is connected to the bus bars, the copper surface of the bus bar will be affected like the copper surface of the shunt. However, if we need very low long-term drift, it might make sense to use a bladed version to protect the resistive alloy. However, a special finish to the copper might not be required because small corrosion on the surface of the copper might not affect the overall resistance of the system. So I think it's important to maintain or to prevent corrosion on the resistive alloy, because this can affect the resistance as well as the TCR, or the temperature drift. If the current through the copper bus bar or the copper bus bar is not generating a reasonable voltage drop, which should be the case, then we don't have any specific recommendations for the copper bus bar finishing.
Okay. What is the preferred way to attach the EB welded metal strip resistors to a copper bus bar?
Definitely screws, because it's the easiest way. But as we showed in the presentation, there are other ways like riveting or clamping, which have their advantages. But I think the first choice of our today's customers are screws.
Great. Well, unfortunately, we've run out of time. We still have many questions, but we're going to have to get back to you via email on those. This concludes today's presentation, and on behalf of Electronic Design, I'd like to thank Bourns for sponsoring today's event, and of course to all of you for joining us. Have a great rest of the day.